Hey guys, and welcome back to another video. In this video, we'll be talking about 2.8 semi-log plots. Alright, so let's get right into it. Alright, so first of all, what even is a semi-log plot? So essentially, a semi-log plot is a way to linearize exponential data, right? So for example, if you had like a regular graph and the data looks something like this, right? Let's just say these are some data points. Then on a semi-log plot, and then on this one, the scale for the x-axis, let's say it's like 1, 2, 3, 4, and then for y-axis as well. And then for a semi-log plot, basically one of the axes is logarithmically scaled. So most of the time it's the y-axis. So x just stays the same, 1, 2, 3, 4. But then y is logarithmically scaled. So for example, we could have like 10, and then it goes to 100, and then it goes to 1,000, and then these are like equal intervals. Okay, and so then now if you should graph the same data on a semi-log plot, it would look linear, right? So it looks something like this. And so that's one of the special qualities about semi-log plots, is that if you're given a semi-log plot and the data on the semi-log plot is linear, then you know that the original data have to have been exponential, right? That's one of the special qualities about semi-log plots. Okay, and like the way like you would see this like on usually is like it would be like the grid lines would be like space, and then they get closer and closer to each other until eventually they just get like almost like they're touching each other, right? So like it's like 1, 2, 3, 4, 5, and so on. And then as you like go up, it's getting closer and closer to each other until you hit 10, and they just resets, and it keeps going like that. Okay, so yeah, that's just basically what semi-log plots are. So now let's do some examples with these. So let's say you're given a table of time and the temperature. Okay, so let's say you're given the following data and you want to graph the data on a regular graph and then on a semi-log plot. Okay, so if we were to just graph this regularly, you have x, y, right? And I'll say that the x scale is like going by 10, so 10, 20, 30, 40, 50, 60, and then we'll say that the y scale is also going by tens. 10, 20, 30, 40, and then 50. Okay? And so if you were to graph all these points, you would get something that looks a little bit like this. Okay? So clearly this is like exponential, right? So this is representing exponential data. So that means that when we go to graph this on the semi-log plot, it should be linear, right? It should appear linear. And so let's do that now. So we have like 10, 100, 1,000, and then we have 10, 50. Okay, and then indeed, if you graph this, you get linear data, right? So essentially, semi-log plot is a way to go from here to there. You're essentially linearizing the data, and that can be super useful in certain circumstances. All right, and then with a lot of these questions or these types of problems, they're also going to want you to they're going to ask you to find a regression equation for the original data. And so the way you do that is like you just put like both of these into your like graphing calculator, like into the lists, and then like run an exponential regression on this. And so go ahead and do that now and put into your calculator, run exponential regression and see what you get. And you should get something close to like y equals 110.947 times 0.935 to the x, right? So your exponential regression should like be somewhat close to this. Okay? And so this is the equation that models this. So what if we want the equation, the graph that models this data, right, to the linear? So you could honestly just take log of both sides, and then you can find log of y. And if you take log of this, and then you can just simplify, right? So here we have this number times this quantity. So we have a log of a product, so we can break that up into addition. So we have log of 110.947 plus log of this. And then I'm just going to skip a step because we have this raised to the x power. So we can take the x out front. So plus x times log of 0.935. And now notice that this is actually just y equals mx plus b form, right? It's just slope-intercept form because we have the slope m times x plus b. It's equal to the y variable, right? And the reason this represents this is, well, first of all, it's in the format of a line, right? It's in the equation of a line. And then second of all, log y is being like logged, right? And that's exactly what's happening to the y-axis. We're taking log of it. It's logarithmically clear. So that's why this is the equation for this line. And if you were to like punch these numbers into the calculator, you should get approximately 2.045 and minus 0.029x, right? So that is the equation that models this graph. And then the other way that you could do this is you could just take log of all these temperature values, like the y values, separately, and then take those values and then the original x values, and then run linear regression on that, and then you'd get that too. You get the same equation. So, but I'll let you test that on your own. Okay. All right. Let's do another one of these examples. All right. So we have x and then y. So go ahead and see if you can graph these on the regular graph and then on the semi-log plot on your own, and then try finding the regression, exponential regression, and then find the linear regression for the linearized graph, and try doing that both ways, right? So first just do it like the algebraic way, we take log of both sides, and then just like take log of each of the y values, and then take the linear regression of the x values and the new y values, right? So go ahead and pause the video and see if you can just do all that. All right. So for the regular graph, I am going to scale my x's by 2, and then I'm going to scale my y's by 200. And you get something that looks like, let's see, right, that's just like a rough sketch. But as you can tell, it's exponential, right? And so then now if we graph this on the semi-log, keep the x scale the same, and then obviously change y scale to logarithmic, and then you should get something that looks like that. All right. So as you can tell, we changed exponential data to linear data. So that's exactly what a semi-log plot is supposed to do. So then now if we run exponential regression, you should get some equation. And then to find the linear equation, because that's what we're more interested in, you would just take log of all the y values, and I'll actually just write that here. So we have, okay, and so then you would want to run linear regression for these x values and then these log y values, right? And so if you run linear regression on that, you should get log y is equal to 0.322x plus 0.360, or something close to that at least. All right. Okay, good. So yeah, that's pretty much it for semi-log plots. The key thing is that if you have a semi-log plot, then and the data appears linear on it, then that means that the original data is exponential, right? That's like the key takeaway from this whole lesson. But if you found this video helpful, please make sure to subscribe and don't forget to leave a like. I'll see you guys in the next video.